Hi everybody. This is Munwar, Assistant Professor of Sri Vidyaniketan Engineering College here in Rampet. So today I am going to discuss about the working of diffie-hellman key exchange. The purpose of this algorithm is to enable two users to exchange a secret key securely. Then that key can be used for subsequent encryption of messages. The diffie-hellman key algorithm depends on discrete logarithms. So before going to define the discrete logarithms, let me define an important parameter that is nothing but a primitive root of a prime number p as one whose powers generate all the integers from 1 to p minus 1. That is, if a is a primitive root of the prime number p, then the numbers a mod p, comma a square mod p, comma a cube mod p, and so on a power p minus 1 mod p are distinct and consists of the integers from 1 through p minus 1 in some permutation. Then we can say that a is a primitive root of p. For any integer b less than p and a primitive root a of prime number p, one can find a unique exponent I such that b is equal to a power I mod p, where 0 is less than or equal to I is less than or equal to p minus 1. Here the exponent I is referred to as the discrete logarithm or index of b for the base a mod p. This can be denoted as the value as d log b base a comma p. Now let's see how this algorithm works. There are two publicly known parameters or numbers are there which are related to this algorithm. One is the prime number q, another one is an integer alpha, that is a primitive root of q. Suppose the user a and b wish to exchange a key. User a selects a random number xa which is less than q and computes ya such that alpha power xa mod q. Similarly, user b independently selects a random integer xb which is less than q and computes yb is equal to alpha power xb mod q. Then each side keeps the x and y values as private, each side keeps the x value as private and makes the y value available publicly to the other side. Then user a computes the key as k is equal to yb power xa mod q and user b computes the key as k is equal to ya power xp mod q. These two calculations produce the identical results and the procedure of producing the results are given below. The final result is that the two sides have exchanged a secret value. Furthermore, because xa and xb are private, an attacker only has the following ingredients to work with. Suppose an attacker is having a q, ya and yb. Thus the attacker is forced to take the discrete logarithm to determine the key. Hence an attacker must compute xb is equal to d into log yb base alpha comma q. The attacker can then calculate the key k in the same manner as user b does. If you observe the security of diffie-hellman key exchange, the security of the diffie-hellman key exchange lies in the fact that it is relatively easy to calculate the exponentials moduli prime and it is very difficult to calculate the discrete logarithms. For large primes, the later task is considered infeasible. Now let's have an example. The key exchange is based on the use of the prime number q is equal to 353 And the primitive root of 353, in this case, let's suppose alpha is equal to 3. A and B selects secret keys XA is equal to 97 and XB is equal to 233 respectively. Then each computes its public key, like A computes YA is equal to 3 power 37 mod 353, which gives the result 40. And B computes YB is equal to 3 power 233 mod 353, which gives the result 248. After this calculation, both the parties exchange the public keys. Each can compute the common secret key as A computes K is equal to YB power XA mod 353, which is equal to 248 power 97 mod 353, which gives the result 160. And B computes K is equal to YA power XP mod 353 is equal to 40 power 233 mod 353 is equal to 160. That means here you can observe both A and B are having the same value 160. We assume an attacker would have available the following information. Q is equal to 353, alpha is equal to 3, YA is equal to 40 and YB is equal to 248. In this example, it would be possible to determine the secret key 160 by brute force. In particular, an attacker E can determine the common key by discovering a solution to the equation 3 power A mod 353 is equal to 40 or the equation 3 power B mod 353 is equal to 248. The brute force approach is to calculate the powers of 3 modulo 353, stopping when the result equals either 40 or 248. The desired answer is reached with the exponent value of 97, which provides 3 power 97 mod 353 equal to 40. But this is infeasible and impractical with large numbers. Thank you.